addresses the apparent contradiction between the idea of an infinite and unformed populating universe and the observed darkness of the night sky. The paradox posits that if the universe were infinite and unchanging, with stars distributed uniformly, every line of sight should eventually intersect with a star, resulting in a night sky as bright as a star's surface. However, this contradicts the dark night sky observed, leading to proposed solutions like the expansion of the universe, finite age of stars, and the presence of interstellar dust. Resolving OLBER'S paradox has contributed to our evolving understanding of cosmology, influencing concepts like the expanding universe and the Big Bang theory.
Theory of OLBER'S paradox. OLBER'S paradox overview. Observation: the night sky appears dark despite the assumption of an infinite and uniformly distributed universe filled with an infinite number of stars. Question: why isn't the night sky ablaze with an infinite amount of light? The second is Heinrich Wilhelm OLBER'S. The paradox is named after the German astronomer Heinrich Wilhelm OLBER'S, who discussed it in the early 19th century. Third one is proposed resolutions. First, universe evolution. The universe is not only infinite but also evolving over time. The second one is expansion effect. As the universe expands, light from distant stars experience a redshift, making it undetectable as visible light to the human eye. The third one is finite age. The cosmos may not be infinitely old, limiting the number of stars whose light has had time to reach us. Redshift explanation. As light travels through expanded space, its wavelength stretch towards the red end of the spectrum, making it harder to detect as visible light. And next, limited observational time. The finite age of the universe restricts the time available for light from distant stars to reach us. And next is combined factors. The combination of an evolving universe, redshift effects, and limited observational time helps explain the observed darkness of the night sky. And the last one is contribution to understanding the cosmos. Resolving OLBER'S paradox with these considerations enhance our understanding of the cosmos and highlights the dynamic nature of the universe, contributing to cosmological theories.
The quantity of light emitted by a star is defined as its absolute brightness. Surface brightness B is defined as luminosity per unit surface and luminous energy radiated per unit time. Assume there are L stars with average brightness. The average density of stars N in a volume V is given by N equals to N over V. If an average star surface area is A, then its brightness is calculated as B equals to L over A. The Sun may be seen as an ordinary star given our familiarity with it. The number of stars in a spherical shell with radius r and thickness dr is given by 4r squared n dr. The total radiation of stars as measured in the start of an infinitely large static universe is calculated by integrating the spherical shells from 0 to infinity. A finite number of visible stars, each with an angle ar squared, may obscure an infinite number of more distant stars. Integrating from 0 to infinity for distant r is incorrect in this context. Limit the integration up to a distance r where star disks equally tile the whole sky covering an angle of 4. OLBER'S paradox arises from the apparent contradiction that despite countless stars, the night sky remains black. OLBER suggests that unseen interplanetary dust might absorb the light, leading to the night sky's darkness. The hypothesis was that starlight intensity would exponentially diminish with distance due to dust absorption, demonstrating that the required amount of dust for absorption would be immense, violating even the sun. Additionally, the heated dust would emit infrared light, making it visible. The paradox is resolved by recognizing the universe's finiteness and evolution over time. In a finite and evolving universe, distant starlight may not have had sufficient time to reach us, and the expansion of the universe explains the darkness of the night sky.
OLBER'S paradox has raised many interesting questions from the aspect about the nature of the universe and has several significant conclusions. So there's four significant that we want to focus in this video.
So, for the first significant is cosmology assumption. So, when the German astronomer raised the question about the dark sky, the first assumption has been made about universe to answer the question, which is stars in finite and uniform and universe is static. But the assumption has been rejected by the modern expert by saying that the stars in infinite but not uniform, and also universe is not static but universe is expansion by the theory of Big Bang. So, for the first significant foreigner is expansion of the universe. First of all, everyone know that the universe had definite beginning at the Big Bang 13.8 billion years ago. The expansion of universe helps solve this paradox. As the galaxies move apart, the light from the star undergoes redshifting, shifting out the visible spectrum. So the expanding universe role in redshifting light connects them. So foreigner is
Cosmic evolution, as we understand it today, is governed largely by the laws of physics, particularly those of thermodynamics. After all, of all the known principles of nature, thermodynamics has perhaps the most to say about the concept of change. Literally, thermodynamics means movement of heat. A more insightful translation in keeping with the wider connotation in Greek antiquity of motion as change would be change of energy. Before 1999, astronomers estimated the universe age to be between 7 and 20 billion years. Edwin Hubble's 1920s discovery of the universe expansion led to the realization that galaxies farther away move faster. By measuring velocities through redshift and distance using Cepheid stars, astronomers calculated the Hubble constant, crucial for estimating the universe age. Ground-based telescope limited distance accuracy. In 1993, the Hubble Space Telescope improved Cepheid distance measurements, yielding a more precise HO. By 1999, astronomers using HST determined HO as 71 km, uncertainty narrowing the universe age range to 9 to 14 billion years based on extrapolations to the Big Bang. This marked a significant advancement in modern astronomy. Before 1999, astronomers estimated
one resolution to the paradox is the finite age of stars. If the universe has an finite age, not every line of sign will intersect with a star, as some stars might not have. The expansions of the universe leads to redshift in the light from distant stars and galaxies. As light travels through expanding space, its wavelength increases, shifting it toward the red end of the spectrum. This can contribute to the dimming of the light from distant objects, making the night sky appear dark. Redshift states that as a star moves away from an observer on Earth, the wavelength of the light emitted from the star will increase and the wave will be stretched. Consequently, the faster the star of the galaxies is moving away, the greater the redshift is. The shortest wavelength of light in the visible spectrum is violet with a wavelength of 390 nanometer, and the longest wavelength human can see through the naked eye is 715 nanometer. This explanation suggests that Olber was correct and the universe is infinitely bright. However, since Hubble did not discover that the universe is expanding until 1929, Olber could not take into account the redshift of stars. The bright light present in the sky at night is not visible to us when we look up, and so this is why we have a dark sky at night. Next, interstellar dust. Interstellar dust consists hydrogen and 1% dust. The presence of interstellar dust can scatter and absorb light, contributing to the darkness of the night sky. Dust particles can block the light from a distant star, preventing it from reaching an observer on Earth. Dust and gas in the interstellar medium can contribute to the obscurations of distant stars through absorption and scattering. There was a various particle in space that can absorb or scatter light as it travels through space. A substantial amount of light can be absorbed by an intervening material if it is sufficient to prevent exposure to our eye. These absorptions and scattering can contribute to the darkness. Next, cosmic microwave background (CMB). NASA has launched 2 satellites to study the CMB in detail. The Cosmic Background Explorer, or COBE, was launched in 1989. It studied the CMB for a number of years. This plot shows that the spectrum of the CMB is exactly the shape of a black body curve emitted by an occupied gas with a temperature of 2.726 Kelvin. The detections of the cosmic microwave background radiation provide evidence of the Big Bang and support the idea that the universe has a finite age. The CMB is the afterglow of the early, hot universe and is observed as a faint glow through the cosmos. However, if this explanation were true, there will have been a point in time billions of years ago when the universe will have been much smaller and the star will have been much closer to the Earth. At this time, the light emitted from the not so distant star will still be in the visible light region of the electromagnetic spectrum. This suggests that in the early years of the universe, sky surrounding the Earth will have been continually light. If this was the case, the light energy from the early stage of Earth must still be present in our universe. Since the light was emitted from this star billions of years ago, the wavelength will have increased vastly as the universe expanded, and therefore, the light will have entered the microwave region of the electromagnetic spectrum.
First, OLBER'S paradox helps us in understanding the universe. The resolution of OLBER'S paradox contributes to our understanding of the nature and of the universe. It prompts scientists to explore and refine cosmological models, which in turn help us comprehend the structure, dynamics, and evolution of the cosmos. Next, OLBER'S paradox has philosophical implication, raising questions about the nature of an infinite and static universe. It encourages contemplation of the fundamental aspect of space, time, and the nature of celestial bodies. Furthermore, OLBER'S paradox may help in technological development. Advances in observational astronomy and technology may be driven by the quest to understand cosmic phenomena, including those related to OLBER'S paradox. Technologies developed for astronomical observation often have broader applications, contributing to technological progress in various fields. And finally, scientific inquiries like OLBER'S paradox can inspire curiosity and wonder about the universe. Such curiosity can drive interest in science, technology, engineering, and mathematics field, encouraging education and exploration.